Okay, got it. Thanks for the invitation and the opportunity to speak here. So this is about a recent project of ours. So together with Paul Jungeblut, who is my PhD student, and Samuel Schneider, who did his bachelor thesis on this topic here, together with me and Paul at the KIT, Karlsruhe Institute of Technology in Germany. I am not an expert in cops and robbers. I haven't been before. This is, I think, the first or second time that I do something about cops and robbers, but it's a fun game. And I like games, and it's a game on graphs, and I like graphs. So I thought it's a fun topic for a bachelor thesis, and then it just grew into a proper topic. And we ended up having a paper which we submitted. And today I'm going to talk about the main result in this paper, and show you along the way what the cops and robber game is and what surrounding and catching means in this context. All right, so cops and robber is a the classical cops and robber game. The board of the game is a graph, like my little graph that I have here. And so the vertices of this graph are the possible position, kind of the squares of the board, the positions for your pieces. And the edges indicate possible moves. Okay, so you can move a piece from vertex to vertex along an edge. And there's two players, which I call player one and player two sometimes, but it's usually the cops player and the robber player. Yeah. And the cops player has K pieces, each of them are cops, and the robber player only has one robber piece. And then let me just start telling you the rules by doing an example at the same time. So for instance, let's say K is a parameter of the game, say K is 2, so we have two cops here. And the game starts by both players seeing the graph, and then the cop player can choose where to position the two cops. So cops start. Initially, they have free placement. And then later on in each turn, they can either move along an edge or stay where they are. And each cop can decide individually. So all of the cops can move, or some can move and some can stay put, and so on. So after seeing the initial placement of the cops, it's the robber's turn. The robber sees where the cops are and places himself on some other vertex or some vertex of the graph. Also no restriction, free choice. And then also whenever it's the robber's turn, he can either stay put or move along an edge. Okay. So now it's the cop's turn. And of course, the cops try to catch the robber. So the goal is that the cops want to go onto the same vertex as the robber. So let me do it a little bit more formally. So we can say that at each time, the state of the game is one particular vertex, which may be called R for the current position of the robber. And then a subset of the vertices may be called C for the current positions of the cops. And strictly speaking, this is a multiset because several cops may also be positioned on the same vertex. And then the game ends with the cops winning when the state of the game fulfills this condition, namely the robber vertex is in the subset of the cop vertices. So meaning that there is a vertex where the robber is, and there's also a cop. Okay, so when the cops catch the robber, the game ends and the cops win. And the robber wins if he can avoid this forever. Okay, so let's try it. So now cops start. They see where the robber is, and so they want to catch him. So maybe they move closer. Yeah. Now it's robber's turn. Robber sees cops approaching, and he can decide to move away. Okay. Cops see where the robber goes, and then they move also closer. Maybe the second cop here goes to the left in order to avoid that the robber goes down. Yeah, if he goes back where he came from, which is allowed, the cop would immediately catch him. If the robber stays where he is, this cop here would immediately catch him. So the only way for the robber to escape is to go there. Okay, then the cops maybe do something like this. The robber cannot stay and the robber cannot go here. So the robber goes up there. Okay, maybe the cops think of a different strategy. They might move here. So whenever he goes here, he's caught. And if he goes here, he's caught. If he goes here, he's not caught. But actually, he can also decide to just stay there because he's not threatened immediately. Yeah. So maybe he decides to just stay there. So cops make a move, robber escapes. And in fact, in this particular graph, you can show, this was by far no proof, it was just an example, but you can show that the robber can actually evade being captured indefinitely. So this graph is a robber win graph, okay, against two cops. By the way, when we talk about, who wins, we always assume that both players, the cop player and the robber player, play perfectly. So they have complete information, they are arbitrarily smart, they can have time to compute whatever they want. So we assume perfect play. And under perfect play, there is exactly one case happening, either the cops win or the robber wins. So this is a robber win graph. Second little disclaimer, for technical reasons, all the graphs that I consider here are connected because the pieces cannot move between connected components. So we just assume that the whole graph is connected so that that the whole board can be visited. Yeah. Okay, so this particular graph, for two cops, the robber wins. Of course, if I increase the number of cops, if I go to 3 cops, the cops get stronger, right? At some point, if I have as many cops as there's vertices, clearly the cops win. So maybe 3 cops are already sufficient. So let's position 3 cops kind of everywhere in the graph to maybe cover as much area as possible. And then let's put the robber there because there he's not immediately caught, at least. And now the cops could do something like this, which again leaves the robber only with one choice, namely to flee to this vertex. And then we can go there and we have a problem. Yeah. So the robber cannot stay here. He would be caught by this cop. He cannot go onto the cop, then he's caught also. He cannot go here, and if he goes there, this cop is there to catch him. Yeah, and you can prove that actually, no matter how the robber tries, if the cops are smart enough, 3 cops are always sufficient to catch the robber on this particular graph. So this is a cop's win now. Okay, so for some k, a graph is a robber win graph, and for some k, a graph is a cop win graph. And of course, this is kind of a monotone parameter. Yeah? So if the cops already win with some k, then with larger k, they still win. And if the robber already wins versus some k cops, then for fewer cops, he still wins. Yeah? So it's really about between 0 cops where the robber certainly wins and the number of vertices cops where the cops certainly win, where exactly is this turning point that the cops start to win. And we decide to call the smallest number of cops that is needed for a cop win the cop number of the graph. And for this talk, I want to denote it by C of G. So this particular graph here, my little example, has a cop number of 3. Okay. All right, let me put you to a test whether you understood the game and the graphs and everything that I just did. So this is a new graph. It's a cycle. Let's say, I don't know how many vertices this has. Let's say it's a long cycle. What's the cop number of this graph? Oh, yeah, I see. So people are showing 2. Yeah, indeed, it's 2. Yeah, 2 cops are certainly necessary, but also sufficient to capture the robber if the robber is smart enough. Okay. Now, let me show you what we actually did. We didn't consider the classical cop number in the first place. We started with a new variant of the game that has been introduced recently. So the rules are basically the same as for the classical variant, but this new variant, which is called a surrounding, and let me call it surrounding vertex variant, just changes the condition of when the cops win. The cops don't win if the robber is on the same vertex as the cop. So it's not that one cop kind of grabs the robber and, you know, puts him to jail or something. Instead, the cops want to surround the robber. So they want to be on all neighboring vertices of the current robber vertex. Formally, you could say that the neighborhood of the current robber vertex, seen as a vertex set of the graph, should be a subset of the set of cops. Okay. Good. And then the corresponding game is played again under perfect play and complete information. There is this turning point where there is enough cops to capture, to surround any smart enough robber. And the smallest number of cop that is necessary and sufficient is called C sub V of the graph. Okay. Now again, maybe this is a little harder. What is C sub V of the cycle?
Still 2, right?
Still 2, you would think so. Everybody thinks, I'm sorry for this mean question, but it's not 2, it's 3. Let me show you why. So here's 2 cops. What do? They approach the robber, right? What does the robber do? The robber does this. He's allowed. He's not caught. He's not surrounded, right? So this condition here is not satisfied. It's not that all the neighbors of the robber vertex are occupied by cops. So maybe if the cops try to really surround him, the robber can still do this. So actually, the robber strategy would be to just stay opposite of one of the 2 cops always. So when one of the cops goes clockwise, the robber does the same. And if he goes counterclockwise, the robber does the same. And this way, this cop cannot get close to the robber, and the other cop alone cannot surround him. But there is another variant, which is maybe a little bit more natural to avoid this weird case, right? And this is called the restricted surrounding vertex variant. It's getting complicated already. So this has the additional rule that the robber may not end his turn on a vertex that is occupied by a cop. So in particular, he may not move onto a vertex where a cop is already standing, because then he ends his turn on a cop. And also, if he stands somewhere and the cop walks onto him, after his turn, he cannot just stay there. He's forced to go away. Yeah, which is a little bit more natural. And in this variant, we have yet another cop number, CVR, R standing for restricted. And the question is, what is the restricted vertex surrounding cop number of the cycle now? Now it's again easier.
I'll try 2 again.
Yes, now it's 2 again. Yeah. So now the thing is, if the cops are like in this position, the robber cannot move onto the cop anymore. And the cops should also not move onto the robber. So they should narrow him down without actually touching him. It would be now a mistake for a cop to move onto the robber. So if they do something like this, then they surround it. Okay. All right, so this is the surrounding cop number and the restricted surrounding cop number of a graph. Okay, the goal of the cops is to surround the robber, meaning that all the neighbors of the current robber's position should be occupied by cops. He has nowhere to go. And there's this maybe restricted version where the robber may not end his turn on a cop to avoid some unusual things. Right? Okay, so there is actually going to be more variants. So the slide already tells you that there's going to be more variants. But before I show you all the like further variants, let's recap and let's compare these things. Yeah. So we have the robber being not restricted, and with the C sub V of G. We have the robber being restricted with the C sub V R of G. Both are surrounding cop numbers, and then there's the classical game with just C of G. Okay. And the question is, how similar are those numbers? Yeah, so we have seen the cycle with this number being 2, this number being 2, and this number being 3. So they are not always the same, but how different are they? So the first observation is the following. Observation 1 is in the restricted variant, the cop number is at most the unrestricted surrounding cop number. Well, of course, I mean, we just put extra restriction on the robber. Just it helps the cops. So it cannot get harder for the cops if the robber is more restricted. Okay, so any strategy that works against an unrestricted robber also works against a restricted robber. Okay, that's easy. The other thing is in the unrestricted variant, there's an easy lower bound, namely delta of G, which is the maximum degree of the graph. So the maximum number of neighbors a vertex can have. Because in the unrestricted variant, it would be a feasible strategy for the robber to just start on a vertex of maximum degree and never move. In order to be surrounded, all its delta of G neighbors should be occupied by cops. So if there's not enough cops available to do this, then he will never be surrounded. This is prevented by the restricted variant. Yeah, for instance, here I have a little graph. This is a K1 delta. Yeah, there's just a star graph with one center and delta leaves around it. And here, indeed, this strategy for the robber just staying in the middle is valid, and you can show that the surrounding cop number of this graph is indeed delta. Yeah, you need delta cops for instance, for this particular graph, 5 cops to surround the robber. But in the restricted variant, 1 cop is enough, because this cop just goes onto the central vertex, and now after the robber's turn, the robber is not allowed to be on a cop vertex, so he must move to a leaf where he is surrounded immediately. Okay, so these restriction and not restriction, this might make a huge difference. Okay, it might be a factor of delta apart. Actually, you can prove that it's always at most a factor of delta apart. Okay, so for every graph, in the unrestricted version, you need at least, at most, delta times as many cops as there are in the restricted version needed. Okay, let me also show you a proof idea of this. So the proof idea is we have to prove an upper bound for a cop number. If we want to prove an upper bound for a cop number, it's always we have to give a strategy for the cops to do, for this many cops to surround the robber, no matter how the robber behaves. And what we do is we take the strategy that we are given realizing this restricted variant cop number and simulate it by just saying for each cop in the unrestricted variant, we just use delta cops in the restricted variant, all moving as a bunch on the same vertex. Okay. So if the robber is surrounded by, in the unrestricted variant, he's still surrounded in the restricted one. But now the robber might make a move that is illegal in the unrestricted, in the restricted variant. Yeah. He might move onto a vertex occupied by a cop. But in this case, I can just spread the cops out from the vertices because it's delta of them and surround them immediately. Okay, so by multiplying each cop to delta cops, I can also deal with the case of unrestricted rubber movement. Okay, I would like to denote this in this little table here by these arrows. Okay, what do I mean by this? So the top arrow basically says I can go from here to here no matter what. So if I have a strategy for the unrestricted variant, I can do the same thing for the restricted variant. Yeah, this is the first observation, this inequality here. Yeah, without increasing my number of cops, the same number of cops still works. And on the other hand, if I have a good strategy, but it's only for restricted robbers, I can go to the unrestricted version by paying a factor of that, paying a factor of maximum degree of the graph. Okay, this is the statement of this lemma. Okay.
Can I ask a question?
Yes, of course. Always.
So this factor of delta can be tied in the case of a star.
Yes.
But do you have examples where the restricted cop number is higher than 1, where you still need this factor of delta?
Yes, yes. I'm not sure whether we have it exactly with delta. Maybe we have it with delta and then -1 in the end or something like this, or times delta -1. But this is essentially tied, I would say.
Okay, thanks.
I was actually, a very good point. I was actually at some point wondering what would be a tight example here in this case, because we have 3 parameters that we are kind of comparing, right? So in order to really say it's exactly this, you would say not only for every cop number, but also for every maximum degree. And then for every combination of those. So I don't know, this we don't have. We don't have it for every combination of those, but we have it for large enough cop numbers for any cop number. Okay, so this, for me, from the extremal point of view, tells the story how these 2 cop numbers relate to one another. Yeah, in the worst case. Let's also link it to the classical game. I mean, this is also an easy observation. So this is now observation 3. This is the classical cop number is at most the surrounding restricted vertex cop number. So the point is, if you manage to surround the robber, and now it's the cop's turn, then you can capture him. Yeah, if it's now the robber turn, he either pauses or he moves onto a cop, and you capture him. Yeah. So if you can surround him, then you can also catch him. But what is not so obvious is whether you can do it the other way around. And we're going to talk about it. Before, let me show you these other variants. So there is another kind of row in the table where we are talking about cops playing on the edges of the graph. Yeah, so then here's a little picture. So the robber is still on the vertices and the cops are on the edges. And the robber is surrounded if the cops occupy all the edges incident to the robber vertex. Yeah. So think of a city, and the robber is always on the crossings, and the cops are blocking streets. Yeah. So if he finds himself on a crossing where all the outgoing streets are blocked by cops, then he's surrounded and caught. There is also, similar as before, a restricted version where in the restricted version, the robber may not traverse through an edge on which a cop is. Yeah, makes sense. So let's do just a quick example. For instance, the robber might go here. Yeah, in an unrestricted version, he might also go here, but then he would be surrounded. So maybe he goes here. And then the cops can do such moves. So cops move from an edge to an adjacent edge, meaning to an edge that has an endpoint shared with the edge before. And in this case, this would be a situation where the robber is surrounded by these three cops. And you can do similar things with comparing these two things. So you can say, okay, how much do I pay for the robber being restricted? So one direction is again easy. So the same number of cops, of course, works because you're only making the robbers weaker. And the other direction, a similar strategy by mimicking the strategy from before with delta cops just works. But you can also compare the vertex and the edge variants with one another. Okay. And let me just quickly tell you a little bit about it. So this lemma here tells you that the vertex cop number, vertex cop surrounding number, is at most twice the edge cop surrounding number. And this holds in the unrestricted setting as well as in the restricted setting on both sides. And let me also show you a little proof idea, and you can figure out the details quite easily. Well, again, we have to find a strategy for vertex cops, given a strategy for edge cops. And well, the obvious thing is if you have an edge cop here, you mimic it by two vertex cops. Yeah, just occupying the two endpoints of the edge. Then you have to check that a move of a cop from an edge to an incident edge is possible for the two cops to mimic. And if the robber is surrounded by edges, then he's also surrounded by the endpoints of the edges. Okay, that's easy. On the other hand, if you have a good strategy for vertices and you seek a good strategy for edges, you have to again pay a factor of delta, roughly. There is examples giving you this. Okay. So this basically puts all these four surrounding numbers into the same say order of magnitude. If you allow yourself like a factor of maximum degree. But this classical game here is only linked in one direction yet. And the question was, can you do it the other way around? Can you say, if you have a good strategy in the classical game where it's sufficient that one cop catches the robber by just being on the same vertex, can you then, by paying a factor of delta maybe, do a surrounding strategy? This has been explicitly asked in a paper published 2020 by Kreutzer, I hope I pronounce it correctly, Komarov and McKay, where they ask it for the restricted edge variant of the game. Yeah. But the same is not clear also for the other variants. Yeah. Can you somehow go from the classical game back to the surrounding game? And maybe now is a good time to talk a little bit about related work. So we didn't make up all these variants. I already said it in the beginning. These have been recently introduced. So the original game is very old. So goes back basically to the PhD thesis of Kiyo, who considered the game for one cop only. Then Nowakovsky and Winkler did the same for one cop only, and then Eigner and Fromme introduced the classical cops and robber game for several cops. And they also introduced the cop number as I have defined it here. Then these surrounding variants are newer. So the edge variant has been proposed in 2015, actually in a technical report. So this is a subset of these authors, and the paper is also a subset of this paper, where they introduced the surrounding edge variant. So it's been around like roughly 8 years or 7-8 years. And the vertex variant also in the restricted setting has been proposed by these guys, a group of 7 authors in 2020, also published in 2020. And I heard one of them giving a talk about it, and this is how I knew about these things. Okay. So yeah, these surrounding variants are rather new. There is not much done about it. There is this one open problem, this conjecture, which is phrased in terms of restricted edge variant. But you can also ask yourself about the other variants. There is a paper by Pavel Pralat who proves this conjecture, who says, yeah, the conjecture is true, at least with high probability for the Erdős-Rényi graph, for GNP. If you have a random graph, then with probability 1, this conjecture is true. But apart from this, nothing has been known. There has been all examples where these COP numbers are computed, they satisfied this inequality. So our result, together with Paul and Samuel, is the answer is no. Actually, we prove that for all k, there's a graph G sub k, whose surrounding COP number is at least k, whose classical COP number is just 2, and his max degree is just 3. So it's not only that it's false, but you cannot bound it by any function of delta and the classical COP number. Yeah, so the classical COP number is 2, the maximum degree is 3, so these are just constant. But as keeping these constants, you can drive the surrounding COP numbers up as you want. Okay, and that's why it also doesn't make any difference whether I put here the classical surrounding COP number unrestricted or restricted, or whether I put any of the other 4, because if one of them is large, the other ones are also large, because they're all linked together. Okay. And this is the plan for the rest of the talk. I want to convince you or give you at least an idea of this construction. How do we do this? Yeah. And I start by showing you the rough idea, which was, for me, the key insight of an effect, a phenomenon, which might be useful to construct such a graph. Okay. And this is a patch of a graph, and we're going to augment it later. But let's consider it. So what do you see here? You see 2 complete balanced binary trees. Yeah. So here on 8 leaves, one on the left and one on the right, and then the corresponding leaves are connected by long paths. So think of these paths as being really, really long. I don't know, 100 vertices or whatever. And then exactly in the middle of these paths, there is kind of a way out, a way to escape to the rest of the graph. Okay. So assume we are in this situation, and I want to argue that how to catch the robber with just 2 COPs. Yeah? So I have to prove to you later that the ordinary COP number in the classical variant is just 2. So assume I somehow brought us to the following situation. The robber is here, this COP is here, and the other COP is here. Yeah, on the kind of the copy of this vertex of the robber. So now it's the robber's turn, and he cannot stay where he is because otherwise he will get caught. So he's kind of chased by the left COP and forced to go down the tree. And if he decides to go down the tree, the COPs do the following. So this COP just goes down to the same branch of the other tree, while the other COP, the left COP, keeps chasing the robber. Okay. And then again, now the robber has kind of 2 ways where to proceed, left or right. And maybe he chooses to go left, and then the other COP also copies it, and he's still being chased. So he can never go back. Once a decision is made, it's final, and the other COP does it. The only way for the robber to escape is to go to one of those middle things and then escape to the graph. So now he kind of decided which exit he wants to take. It's robber's turn now. he can go and be there first, but immediately when he reaches there, this cop will also be there and catch him. Yeah. So he can be there at the same time, kind of, like immediately after the robber. Not before the robber, but after the robber. Okay. So this is how two cops catch the robber. Let me show you why k-1 cops cannot surround the robber. Okay, what is k? So k is the number of leaves in this binary tree. So in my example, this is 8, yeah, because it has height 3, the tree. So later on, it's just going to be a power of 2. Yeah. Okay, and so I have here k is 8, so I have 7 cops. Yeah, and the task is to surround him. And I even don't use the cop that chases the robber from behind. I'm gonna assume that the robber will go down the tree and exit through one of those things. And these cops are here, and they want to prevent him from exiting this little gadget. Okay, so it's robber's turn. What does he do? Robber considers the 2 options that he has. He has the option to go up or down. He considers on the other side the 2 subtrees. Since in total there is k-1 cops, so less than k cops, one of the 2 subtrees has less than k over 2 cops. So there is less threat for the robber, and the robber decides to go where there is fewer cops on the other side. Now it's the cops' turn. The cops see the decision of the robber and they can do whatever they want. Yeah. So maybe they go down in the subtree, or like one cop decides to move along this path. But remember, this path is super, super long. Yeah. So this takes 100 steps to get back to the other side. By then the robber escaped already. Yeah. Now it's again the robber's turn. Robber can see the 2 subtrees now having in total 4 possible exits, 4 leaves. But since before there were less than k over 2 cops, less than 4 cops, now in one of the 2 subtrees, there's less than k over 4 cops. And he goes to this side. And again, the cops move. And the thing is, the cops try to be at this exit point before the robber is there, because they want to surround him. So also the way to out of the exit has to be guarded by a cop. But there's too few cops to cover all the possibilities for the robber. So now the robber sees where there is in these 2 subtrees where there's less than k over 8, so in this case less than 1, so no cop. And he goes there. So there might be a cop here which sees this and also goes there. But remember, he will be only there the step after the robber is there, which is not enough to surround him and enough for the robber to escape to the rest of the graph. Okay. So that's the rough idea. Questions?
Yeah, I have a bit of naive question more about the classical, like the argument for the classical number of cops. So it just felt a bit since when the game starts, the robber player puts the robber already, like seeing the configuration of cops, yes. Like just it seems that somehow like the robber was put like in a like, why not to put cop closer to robber closer to the exit, like.
Yes. This is, I mean, I didn't show you how this gadget, I mean, I'm gonna have many of those gadgets and they are combined. Let's just assume we are in this situation, and you're gonna see in a minute how this situation shows up in a larger graph.
Okay.
Okay, but if we are in this situation, you follow the logic. Okay, good. Okay, so let me catch the robber once again. Let me show you once again that the robber cannot be surrounded by carefully looking at the configuration of the cops on the other side. Here, I'm also assuming that there's no cops here, for instance. Yeah. And I have to justify this at some point. Okay, so he can escape. So this is the rough idea. Now, let me show you the construction. I give you the full construction, but I don't give you all the details of the proof. Okay, construction goes in several steps. So what do we want to do? We want to construct a graph GK with the property that for the surrounding version, I need at least k cops. So k minus 1 are not enough to surround him. Classical version, 2 cops are enough to just catch him. Maximum degree should be bounded at most 3. And I'm going to do this only for powers of 2. Yeah, it's enough for me to assume that k is a power of 2. So let's say k is 2 to the s minus 1. And think of s as being a small number. Yeah? It's roughly log k. So s is a small number. Good. That's why it shows s. What is the first step? First step is we take what we call a base graph for the construction, and let me call it h. This is going to be a graph that is 2k regular. So k is some number, some power of 2 actually. So think of 2 in this case. So then it's a 4 regular graph. And it should have what we call girth, at least 5. And girth is a fancy word. It just means that there is no 3 cycles, no triangles in the graph, and also no 4 cycles in the graph. So all the cycles have length at least 5. So those creatures exist. So this is actually the smallest 4 regular graph that doesn't have triangles and 4 cycles, and it's already quite complicated, but we don't really care about how this graph looks. All that we need is that it's 2k regular and it has no triangles and no 4 cycles. And these things exist. It is also easy to construct inductively. What we then take from the base graph, so it's 2k regular. If you know a little bit of graph theory, so this is an even number for sure. So you can find a so-called k orientation. So you can orient the edges, give every edge a direction just in your head, so that every vertex has half outgoing and half incoming edges. So it was 2k regular, so every vertex had 2k incident edges. So now it has exactly k outgoing and exactly k incoming edges. For instance, take a Eulerian tour through your graph and just orient it like this. So then this would do it. So fix any such k orientation of the space graph. Now, step 2 is we replace a vertex. So now a vertex of the base graph looks like this. Yeah? It has like k incoming edges and k outgoing edges. And we replace it with this little patch. These are 2 binary trees, full balanced binary trees with k leaves each. One for the outgoing edges and one for the incoming edges, and the roots are connected by one vertex, which I keep using as white here. And when I have an edge in the base graph between 2 such high degree vertices, and it also has an orientation, then I take this 2 binary tree patch here and this 2 binary tree patch here. So there is one leaf that corresponds to this outgoing edge in this vertex, and there's also one leaf in the lower vertex here that corresponds to the incoming edge. So you replace it by a path and by a long path. So the path has length L, and what L is exactly doesn't matter. All that you need to know is that L is long and S is short. So L is much, much longer than S. All right. This is step 2. Note that if I do this, the graph has maximum degree 3. The the base graph had large maximum degree, had degree 2k, but now everything looks like this. So here's lots of degree 3 vertices and 1 degree 2 vertex, and then here lots of degree 2 vertices. Okay. But I'm not done yet. What I take is I take 2 copies of this graph, H1 and H2. It's the same graph. Yeah, one is up here and one is up here. But I also connect the copies by taking these long paths that replace the edges, yeah, and I assume that this L is, I don't know, odd, yeah, so that there's a middle edge. And the middle edge, I identify the middle edges. I pinch these 2 paths in the middle together. And I do this simultaneously for all the edges. Actually, for every edge that is in this copy here, always when I am in the middle, I have this shared with the lower copy, and then it goes up. Yeah. So, but it's very hard to draw. So that's my attempt. This is step 3. Still, it has maximum degree 3. And it's now in some new degree 3 vertices here appear. Last step, step 4, I take from the upper copy, from H1, from every vertex, namely from the white vertices. So these are this degree 2 vertex here. I make a path of length m, and m is a number that is medium sized. So it's smaller than L, but much larger than S. Okay. So when I have S, I take m very large, and then I take L very large compared to m. And these paths, they end in these vertices, which I just combine into a cycle in any order that you want. So how long is the cycle? This cycle has now 1 vertex for every original vertex of my base graph. So the length of this cycle is the number of vertices of my base graph, and I want to choose it like here. So actually starting with K, I compute S. It's a small number. I take a base graph, which will be automatically very large compared to S. Then I choose M very large compared to this number of vertices. And then I choose L very large compared to this M. Okay. That's the construction. Okay. And I claim this does the job. And what does it mean? It does the job. Well, it means the surrounding cop number should be at least K. I'm not assuming that you should see this now. The classical cop number is just 2. I also not assume that you see this. And the maximum degree of this graph is just 3. I assume that you can verify this. Okay, so let's put a check there. Okay. And let me try to convince you of this fact that the cop number, the classical cop number of this graph is indeed just 2. So I show you a strategy for 2 cops to capture the robber, no matter how he does. The cops start on the cycle, somewhere on the cycle. It doesn't matter. And my general idea is, first of all, I want to push the robber down in this graph. So if he's on the cycle, I want to push him into the H1 copy. And if he's in the H1 copy, I want to push him to H2 copy. Yeah. So if he starts in H2, I'm happy already. Or if he starts in H1, I'm happy already. So let's assume that he starts on the cycle. Yeah. So I want to push him out of the cycle. So what can I do? Well, it's obvious. Yeah, I can just say one cop stays where he is, and the other cop just goes after the robber. Yeah. So what can the robber do? He cannot come towards me. He's going to be caught. He cannot escape. He's going to run to the other cop. So at some point, he must decide to go down. Yeah, and remember, he cannot come back up again, because this here is m long, and m is much longer than the cycle is long. So even by the time he really reached H1, I'm already on top of him. So I can assume that I'm at the top end of a path that the robber is currently moving down on. Okay. Now I can bring the other cop to the same thing. Still, I have plenty of time because M is so long. Robber is still not there yet. Yeah. Okay. Now I let the robber go down. I go after him in order to just prevent him from staying where he is. So I leave one cop up, and the other cop just goes towards the robber to just force him to move. So what does this move look like? So at some point, he's entering this white vertex here of one of those guys. And then he's forced to continue moving. So he's forced to go down this tree. Maybe if the distance is still large, he can, backtrack or whatever. But at some point, he must go out of this blue bubble and enter one such long path. So at some point, it looks like this. And the path is so long, yeah, because L is so large, that in the meantime, this cop can traverse the entire M long path and go on the same long stretch here. The other cop is still up here. Now, the robber is still on this long path. And it's still so long that the other cop has plenty of time to go along the cycle, to go to the other end of this path that the robber chose, go down here and kind of wait for him on the other side. Yeah. So what's now happening? Yeah? So the robber is here. One cop is chasing him, forcing him to move. The robber has to go down to the second cop. Yeah. So he goes down to the second copy. He can either go like to the left here or to the right. What I am guaranteed to have is that the robber is at some point on a vertex in the second copy. And one of the two cops is on the same respective vertex in the first copy. Kind of on the shadow of the robber. So exactly vertical of one another. Either it's this guy or it's this guy. And from this moment on, this cop will continue just to copy the moves of the robber in the second copy. Whatever move the robber does in H2, this cop does in H1, always staying on top of him, going there. And the other cop just goes always towards the robber to force him moving. So they do, yeah. So at some point, the robber walks through this graph. The same is copied by this cop here. At some point, the robber must traverse such a long path. Yeah. And this cop here is on the same vertex. So at some point, the robber will be on this joint thing, and the cop will catch him. Okay. So two cops are sufficient to capture the robber on this graph. And also two cops are necessary, but that's not the point here. All right. So the question is, why is the surrounding variant now difficult for the cops? And why is this at least K? Okay, in order to do this, let me tidy up a little bit. This was all that we need from step one. This was no triangles, no four cycles. We didn't use this before, and this is needed now. And this was the essential part that you have to remember from step two. We have these binary trees here. And step 3 and 4, they'll basically look like this. Yeah. Now I have to prove this lower bound on the cop number. I have to prove to you that K-1 cops are not sufficient to surround the robber. So I have to give you a robber strategy against any K-1 cops. And the robber strategy is he's only in copy H2. He will just be down here. and not use H1 and not use the cycle. He will just be in H2, and he will try to ensure that he's always on such a vertex here, on such a wide vertex, where on the forward and the outgoing arcs, I don't have any cops in my copy here. There might be copies on H1, and these are actually the most threatening ones that I have to avoid. So my strategy is always go forward along directed edges, go to this middle part, but then stay in H2. Yeah, and you go inside into one vertex, so you come, I don't know, up here, and then again choose a way down to the next, go to some other vertex, come back in here, and so on. Yeah, so this is how the strategy looks like. The question is just, where do I go when I'm here at this vertex? And this is, I hope you remember, the same situation that I had in my gadget. I have k options with these trees. I have only k-1 cops. No matter how they are distributed here, I consider the subtree that has less cops, make one step, look what the cops do, consider the subtree that has less cops, make one step, and so on. And I can guarantee to find a way, an exit back into the graph. It might be that a cop is on my vertex always after the cop's turn, but I keep moving. So it might be that one or more cops I have constantly in my back. But I will never be surrounded. The point is the cops will not be able to be at some vertex before me. They can just be there after me. And that's why I cannot get surrounded. And that's why the cop number should be at least k. This was very rough. There's details, but I hope you got the rough idea. So let me just conclude with showing you the slide once more, summarizing surrounding variants of cops and robbers. We have seen vertex versions, also that there's edge versions. I just introduced them because of this conjecture, because this was made in terms of the edge version. They're basically all equivalent if you have the maximum degree bounded. And the question was whether these are also equivalent to the classical game, and the answer is no. We constructed a severe family of examples showing that the classical game can be really easy, while the surrounding variant can be really hard. That's it for me. Thanks for your attention, and I'm happy to answer any questions.
Okay, thank you very much for your wonderful talk. Let's thank the speaker, first of all. I assume there might be questions from the audience, so who wants to ask their question first?
I have a bit of a question. So, sorry, can you hear me?
Yes.
Oh, okay. I guess graph orientations came up somewhere already, but in the general cops and robbers question, like, has there been working like on like directed graphs, or like what happens to that out?
Yes. So you're asking about the classical cops and robber game on directed graphs?
Yeah, or
Yes.
or like the restrictions and so on.
Yes. Yes. I mean, for the surrounding variant, I haven't seen anything for directed graphs. But in the classical version, okay, so there's actually one sentence that I should have put in my talk, namely, Cops and Robber is a game. This has countless variants in the literature. Everything that you can think of has been done, kind of.
Okay.
So there is variants on directed graphs. There is variants where the robber has different speed than the cops. There's variant where several robbers. There's variants where the robber is invisible, whatever.
Oh my gosh.
If I would estimate, it's at least a 3-digit number of variants that is out there from cops and robber. So whatever you suggest, the answer is probably yes.
I was thinking maybe more about the restricted thing, but I guess it's, yeah, okay, thanks.
Yeah, but yeah, I mean, and
Yeah, but yeah, it seems like
yeah, I don't want to say that this is a bad thing. I mean, after all, now we introduced another, or we
yeah, of
considered
course.
another variant, and have another paper on this topic. It's more a good thing about the game. The game is so interesting that even in variants, you can really encounter something. Yeah? And so what I should, for instance, mention is that the most important and most well-known variant besides the classical one is where the cops have helicopters. They can freely relocate themselves in the graphs. And the robber has infinite speed. So he can, yes, move along the edges, but can do so infinitely fast. And this variant, if you then compute the corresponding number of cops, is exactly the tree width of the graph. So you can characterize tree widths by playing cops and robber in a certain variant. And there is also very new structural graph parameters that are also equivalent to certain cops and robber games. So I think it's worth it to consider those variants and to learn something about graphs along the way. So I would definitely recommend looking into directed versions of surrounding cops and robber. I didn't do it.
Do we know some dependence of the number of cops from the number of cycles in the graph?
Number of cycles in the graph? No, I don't. But I guess there is something. I mean, the number of cycles can be really hard to compute, of course. So what is the famous open problem for the classical version of cops and robber is how many cops do you need at most in the worst case, depending on the number of vertices of the graph. Remember that we're talking about the connected graph, and it's mainly its conjecture, long open, very important conjecture, that says that the number of cops that you need in the classical variant is at most of the order square root of n. And it's wide open. There is examples where you need order square root of n cops, but it's not known whether whether this is always sufficient.
Thank you.
I have a question from kind of a complexity theory point of view, which is how hard are these numbers to compute? I guess most of them are hard. Are there any cases where it's not hard?
Ooh. Yeah, I think you can. I think you can compute cop number, so you can decide whether the cop number is 1, the classical cop number is 1 of a graph in poly time. So these have been characterized by this French guy and Nowakovsky and Winkler. So these are called dismantable graphs. So there's an easy inductive construction thing that you can easily recognize. Later, I would guess, but I'm not sure, but I would guess that already with deciding cop number 2 or 3, it should be hard. And in these games, it's usually p-space hard.
Or p-space complete, I guess.
Yes, p-space complete.
Okay.
Yes.
So you don't know of any variant where these numbers are easier to compute?
No, but I didn't see. But I mean, yeah, I didn't consider many variants, so I don't know about it.
Thanks.
Okay, are there any more questions? That doesn't seem to be the case, so I will stop the recording.